Okay, so it's the late 1960s, and I'm studying physics, and I get an invite to a dinner from a professor by the name of John Wheeler. I'd heard of the guy, he was famous, but I really didn't know what he was doing. So I'm sitting there having dinner with him and a couple of the other undergraduates, but little did we realize that John Wheeler was wrestling to come up with a name for some object that he had been working on for years. And within 2 years, he'd come up with that name, and it was black hole. I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. In astronomy and cosmology, most things are discovered rather than predicted. But sometimes, not often, it works the other way. Someone has an idea, occasionally a radical idea, something they think might be true on the basis of known science. And eventually, years, decades, even centuries later, those some things have been found. Some of those ideas in history have been considered outrageous or improbable, but a few, if you go back far enough, were actually scandalous, even punishable by death. In this episode, predictions about the universe that were far ahead of their time, that today are among the most exciting of major research endeavors. It's radical cosmology.
This is a story of a dangerous scientific idea. It's also about vindication, although that was a long time in coming. But it reminds us that there was a time when some ideas about the universe were so controversial, so against the established wisdom, that punishment for talking about them was the ultimate punishment.
This idea challenged our uniqueness in the cosmos. For a long time, since Aristotle, in fact, we thought our solar system and the Earth's place in it was a one and only. That is, there was one solar system in the cosmos, and we were at its center. The moon, the sun, and the visible planets all orbited Earth.
Now, jumping into the modern era, the idea of exoplanets, that is, planets orbiting other stars, was tossed into the astronomical ring a century ago, but there was no evidence until the early 1990s.
Then the Kepler Space Telescope came along, and by the time it retired in 2018, we had learned that exoplanets are common. More than 3,000 planets orbiting other stars have been discovered, and indeed, we've learned that most stars have such worlds.
For science historian Alberto Martinez at the University of Texas in Austin, each and every discovery of an extrasolar planet vindicates the ideas of a 16th century astronomer and Dominican friar.
Giordano Bruno was a philosopher working mainly in the 1580s who believed that neither the sun nor the earth are the center of the universe, but instead the stars are suns surrounded by planets, even having living life forms.
Indeed, our recent discovery of the multitude of planets around other suns strengthens the possibility that life could exist elsewhere. But to think and speak of that idea in the 16th century was dangerous.
He gets in trouble with the Catholic Church because, in fact, the Catholic Church believed that it was a heresy, a religious crime, to believe that many worlds exist.
In 1600, the Church found Giordano Bruno guilty of heresy. He was arrested, tried, and burned at the stake in Rome. For decades, historians and writers have claimed that Bruno was not executed for his beliefs about cosmology, but for purely religious transgressions. But Dr. Martinez says this is because many primary sources hadn't been analyzed. Some were lost, some scattered among different archives. These primary sources included transcripts of the trial and a document called the Sommario, which were transcripts of the proceedings of Rome during the time. After analyzing these documents and more, Dr. Martinez is putting forth a counter-argument.
I have found evidence in primary sources in Italian and Latin that indeed Bruno's beliefs about many worlds are what got him in trouble with the Inquisition.
Bruno's ideas about innumerable worlds were radical in the sense that they challenged the fundamental religious beliefs of the time, that there was but one world. The implications were far-reaching. Dr. Martinez tells the story in his book, Burned Alive, Giordano Bruno, Galileo, and the Inquisition.
Well, Giordano Bruno was an Italian philosopher who lived in the Renaissance, worked mainly in the 1580s. He becomes fascinated by Copernicus's account of the universe. He's one of the earliest ones that takes him up, but he doesn't just support him. He actually develops a greater, broader view of the universe, which is the sun is not the center of the universe at all, which is what Copernicus believed, but instead he believed that the sun is just one of so many stars, an average star. But there are also innumerably many planets, and some of these distant worlds are inhabited.
So just to put this within its historical time frame, he's making these statements years, or he's thinking these things years before the Vatican admonished Galileo.
That's right. It was not unusual for a religious man such as himself, that is, he was a friar, to actually become involved in these things. For example, Copernicus was a canon of the church, which means an employee of the religious bureaucracy. Similarly, numerous other people who were, say, Jesuits, were actively working on, say, cosmology or astronomy, whether it be observational or philosophical.
Giordano Bruno had no means by which to confirm his theories in the late 1500s. So how did these ideas come into his head that there are other stars with planets orbiting them, and perhaps even that they were inhabited?
It's an interesting question. He doesn't clearly explain how. However, there are a series of analogies and even philosophical or theological arguments that he gives. For example, he does not think that the sun is a powerful enough source of light to illuminate the entire cosmos. Therefore, he thinks that it's being illuminated also by other stars, and that the stars are likewise suns. There are even theological arguments. The idea that if God is all-powerful, then he creates infinitely. Why would an all-powerful God settle for one sun, one earth, one moon? That just makes no sense to him. And interestingly, it turned out that his overall description of these planets and star systems is correct.
So we can imagine Bruno not looking through a telescope and examining the planets in our solar system, but really this was a thought experiment on his part. Perhaps he was looking up at the sky, but then sitting, we could imagine, quietly and thinking about the structure of the universe. That's what was going on.
Absolutely. He's not an observational astronomer like Tycho Brahe. But the sorts of things that he does are somewhat similar to the things that Galileo does, only that Galileo does have one advantage that turns him into an observational astronomer, which is he has the telescope.
Well, there's no controversy that Bruno believed these things in the plurality of worlds, but there has been debate over the reason he was put to death. Not all historians believe that it was his belief in exoplanets. Of course, he wouldn't have called them that then. That was the reason he was burned at the stake. Why is this a debate?
The Inquisition is a highly secretive institution, so nothing about the trial was known for decades after Bruno's death, except to people who were close at hand and were involved, and who certainly wrote some things. There being no records, they thought, say in the first half of the 20th century, they thought that he was probably burned for some religious beliefs, but eventually, by the 19th century, when historians are writing about Giordano Bruno, they start entertaining this possibility that perhaps Bruno had been burned for some of his beliefs, which resemble the beliefs of Copernicus or Galileo. By 1942, Angelo Mercati had found in files in the Vatican the extant summaries of the trial of Giordano Bruno, basically 260-odd paragraphs summarizing 300 folios, that is 600 pages, and giving us detailed accounts of objections, accusations, and Giordano's defense over a number of years. But when I analyzed that source and numerous others, I found to the contrary that the accusation of many worlds was in fact the most recurring accusation in Bruno's trial. What they had not done, what nobody in church history or in history of science had done, is actually look at manuals by the Inquisition about what are the specific crimes. When I did, I discovered to my surprise that in the 1590s it was actually a heresy to believe that innumerably many worlds exist, verbatim, and that is what he said, both in his books and on his trial.
So it was actually written down that it was a heresy.
Yes, this is one of the things thou shalt not do.
Now, let's go back to how he was discovered and arrested by the Catholic Inquisition. How did his theories become known by the Vatican?
Well, Giordano Bruno, during the time he's writing, does not live in Italy. He lives in other places, such as England. He gets an offer from a Venetian aristocrat to go teach him philosophy, the art of memory. So he travels to Venice, which is a needless, dangerous thing to do because Venice is connected to the Roman Catholic Church. He travels back to Venice. There, the guy who is his employer becomes annoyed at him because he claims that Giordano Bruno is teaching him or arguing all kinds of weird things. What gets the Inquisition involved, initially the Inquisition in Venice, are the particular accusations of one man. It's, there has to be a process. Somebody has to accuse you. This man accuses Giordano. He becomes arrested, incarcerated. And then the inquisitors begin a process of interrogating him, asking him, did you really say this? Did you really say that there are innumerably many worlds, many suns, many star systems? And he says, yes, I said that, and I believe it. And he doesn't seem to know at the moment that it's a heresy to believe that innumerably many worlds exist.
How is it possible that Giordano Bruno didn't know that what he was saying was heretical?
He didn't know in the same way that most historians of science did not know it. Basically, you have to actually read inquisitorial manuals. Most people I know have never read one. Books were not as available in the 1590s. So not everybody who's just walking around, has access to, procedural codes of law of the Roman Catholic Church. People who specialized on knowing such thing are people like the consultors of the Inquisition and the inquisitors themselves.
Why was his belief in the existence of many worlds threatening to Catholic dogma?
There are several reasons that one can find in various texts, but these are texts throughout the centuries. It's not as though, as they're asking him about this, they say this is repulsive to us for the following reasons. So they don't explain themselves, at least in the sources that we have. But if we look at other sources that are from that time, subsequent or previous, we find, for example, that Catholics thought that such beliefs, many worlds, many Earths, go against the fundamental structure of Genesis. They challenge the question of salvation through Christ. If other people exist in other worlds, how will Christ communicate with them? Would Christ have to be crucified in infinitely many worlds? These kinds of ideas are deeply offensive to Catholics at the time.
I think you point out that one of the inquisitors who confronted Bruno would go on to confront Galileo. Is that right? And would Bruno have known Galileo?
Giordano Bruno apparently never met Galileo, although they overlapped. For example, at one time, Galileo gets a job that Bruno wanted. I mean, it's very interesting. So they're in the same world, and Galileo is certainly aware of Bruno's execution, although he never writes about this. This is a well-known fact. Many other people write about it, and in a sense, the shadow of Bruno's death hangs over philosophers in the early 17th century. Cardinal Robert Bellarmine is one of the original consultors that is present at the very first meeting of Bruno, in which he is told by the Inquisition he was admonished to abandon his belief of many diverse worlds. That same man, Cardinal Consultor Bellarmine, he later ends up confronting Galileo in 1616. So it's certainly an interesting coincidence.
Bruno was burned at the stake in 1600. It would have been a horrific death. What did the Catholic Inquisition gain by burning Bruno publicly, by executing him publicly?
The Catholic Inquisition sees itself not just as a punitive institution, but also as an educational one. They're trying to educate these heretics into changing their mind. When the heretic fails to change their mind, as in the case of Giordano Bruno, they burn him alive, not just as a punishment, but as a way to show the people publicly what the Romans do to people who do things that are grossly offensive against the church. This was very rare. The church in Rome did not go around burning people every year. So it was very rare that they actually did this to him, which shows that they believed that his crimes, his transgressions, were unusually egregious and should stand as a warning for other people who might consider the same.
Well, finally, Alberto, today the TESS mission will follow up on the Kepler Space Telescope to hunt for extrasolar planets. Of course, now we know that there are thousands out there. Well, there are more than thousands, but we've discovered thousands. Their discovery has changed our ideas about the possibility of life on Earth. What do you think Giordano Bruno would have said about these missions?
Giordano Bruno would have loved it. I mean, he was all about the idea that, we're not alone in the universe. There are these other beings. They might resemble us. They might be rational. It would be conceivable to travel there to meet them. As I mentioned somewhere, it's unfortunate. It's too bad that the Kepler telescope was not called the Bruno telescope because, after all, Kepler did not believe in exoplanets, and he, in fact, denied they even exist. Whereas Giordano Bruno did affirm repeatedly that they exist before they were even visible.
Maybe one day the Bruno Space Telescope will be launched. Alberto Martinez, thank you so much for speaking with us.
Thank you, Molly. It's been a pleasure.
Alberto Martinez is a science historian at the University of Texas at Austin. His book is Burned Alive, Giordano Bruno, Galileo, and the Inquisition.
You heard that Alberto Martinez referred to what Bruno was studying as cosmology because the solar system then, in the 16th century, was all that we knew about the universe.
I have to say, it's too bad for Bruno that he didn't, chatter about this stuff 10 years later, because Galileo did. In 1610, he went to trial at the Inquisition, but they didn't burn him. So Bruno pays the ultimate price for having modern ideas, if you will. And that sends a shockwave through Europe because, this guy was a man of ideas. And I think, in a sense, he didn't die for naught, because that shockwave probably encouraged the Renaissance thinking that brought science to the fore. You could liken it to the Salem witch trials, which even 5 years later were so repudiated by people of reason that it never happened again. In the modern era, predictions in science are generally less severely punished, but they can still be disruptive. In the 1930s, another European dared to predict some things that had never been seen, indeed, never even imagined. Today, those objects are on the forefront of research when we can catch them.
I work on tiny particles. They go through almost everything, hardly interact. They come from far places in the universe, and we can learn a lot about the cosmos by studying them.
More prescient ideas about the cosmos that shook up the science status quo.
It's Radical Cosmology on Big Picture Science. Can't wait for the next episode to drop? Well, be one of the first to listen to Big Picture Science a day early, only on Himalaya. Himalaya is a brand new podcast app where you can find every single podcast you love and some future faves. Whether you're a podcaster or a fan, Himalaya's got your back. Discover personally curated playlists and show your favorite podcasters some love with Himalaya's tip jar. It's free, it's the easiest to use, and we're adding cool new features every day. Go to your app store, download Himalaya, that's Himalaya, and don't forget to follow Big Picture Science once you're there. We've been talking in this episode of Big Picture Science about ideas in astronomy that were so ahead of their time, they truly challenged our understandings. This next radical idea was proposed to account for some energy that had apparently gone missing. But the physicist who offered this idea in 1930 did so reluctantly because he thought it was impossible to prove.
In fact, he wrote in his journal, "I have done something very bad today by proposing a particle that cannot be detected. It's something no theorist should ever do."
But Wolfgang Pauli needed a reason for why his calculations weren't adding up. He had discovered that during a certain kind of radioactive decay, energy was lost, gone missing. But due to the law of the conservation of energy, it had to be somewhere. Reluctantly, the Austrian physicist proposed what he called a desperate remedy. He suggested that during this decay, not only well-known electrons were shed, but an energetic lightweight particle as well.
The particle with almost no mass became known as the ghost particle. Today we use the name physicist Enrico Fermi gave to it, meaning little neutral one, neutrino. because it carries no electrical charge. Although Pauli could hardly believe that neutrinos actually existed, his theory was vindicated when they were discovered more than 24 years later. And now we know that neutrinos are everywhere.
Neutrinos are very, very light particles believed to have very, very little mass. And we're continuously bombarded by neutrinos arriving from the sun. In any 1 second, if you look at your fingernail, probably 65 billion, with a B, neutrinos will have passed through your thumb.
Today, these most elusive particles are at the cutting edge of cosmology and astronomy because they're reliable messengers from the universe. They travel for billions of light years unhindered from their source, and that means they can tell us a lot, if we can catch them.
Neutrinos are really, really hard to catch because they interact really rarely with any matter. They only interact through what we call the weak force, and the weak force is, how the name says, very weak, so they can cross the entire Earth or even our entire galaxy without leaving a trace. My name is Anne Schukraft. I'm a scientist. I work at Fermi National Laboratory by Chicago in Illinois, and I'm a neutrino physicist.
It turns out that since neutrinos interact so weakly and so infrequently, that we need very, very big detectors to detect them. So one of them is this ice cube, which is a cubic kilometer of ice, which detects neutrinos which come from, well, wherever they come from. The other big neutrino detector is Super Kamiokande in Japan. The large size needed for both of these kinds of detectors reflects how weakly neutrinos interact with anything, so we need a lot of stuff to try to capture them.
And now, Purdue University physicist Ephraim Fishbach answers what sounds like the setup to a joke. How many cubic feet of water does it take to catch a neutrino?
That's a good question. So let's take Super Kamiokande as an example. The volume of water it has is equivalent to having a cube of water at a football field from the 0-yard line all the way to the 50-yard line in all dimensions. That's how big this cube is. And that cube will detect perhaps 20 or so neutrinos in a day. That's all. That's all you see. With this 50,000 tons of water, you get perhaps 20 neutrinos a day.
That's out of the trillions of neutrinos passing through every second. Dr. Fishbach has his own radical idea about neutrino detection, which he'll share with us later.
Neutrinos have a number of sources, including the sun, but perhaps the most interesting ones are those producing the high-energy neutrinos in deep space, in environments we know little about. Neutrinos that are messengers from the far reaches of the cosmos have a lot to tell us. For example, they might answer the biggest puzzle in physics. Why is there any matter in the universe at all?
That big cubic kilometer of ice catching those ghost particles that Dr. Fishbach mentioned is the Ice Cube Neutrino Observatory, located at the South Pole and run by the University of Wisconsin. In July 2018, the Ice Cube team announced it had scored a big hit, the first detection of one of those high-energy neutrinos from what's called a Blazar. Now, Blazar sounds like something you need to don before going into a fancy restaurant, but in this case, it's a giant elliptical galaxy that has a massive black hole at its center.
Anna Schukraft is working on a new mega-science neutrino project at Fermilab, the Deep Underground Neutrino Experiment, or Dune. But she worked with IceCube for her PhD, and she shares the team's excitement over the detection of a high-energy neutrino.
Yeah, and that neutrino was so interesting because it had such a high energy. That's very unique. We see a lot of neutrinos every day from sources nearby, like the sun or our own atmosphere, but they're lower in energy. So this particular event detected by the IceCube experiment was so high in energy that it was something special. And because it was so rare, people looked into it and sent out alerts for other experiments to look if they saw something interesting at the same time or at the same place in the sky.
I see. Now, in order to detect that single neutrino there, the high-energy one, you were using IceCube. Now, how does IceCube find neutrinos? Obviously, it doesn't have little bags or anything like that. What does it do to detect a neutrino?
So IceCube is an experiment that looks for the traces of light. So in the rare case that a neutrino interacts with matter, it will create other particles, and these particles are charged so they can produce a trace of light. So IceCube uses a transparent medium so this light can propagate and we can detect it with sensors, and that's the ice at the South Pole where IceCube is located. And it consists of light sensors frozen underneath the surface in Antarctica. And this volume, this densely instrumented volume of sensors will then record the light from the secondary particles that the neutrino generated, and that's how we find them.
Okay, let me see if I've got this straight then. So you have this big block of ice, pretty transparent ice, under the South Pole there, a kilometer on a side. Neutrinos are coming in, and one of them, by chance, unlucky chance for this neutrino, I suppose, actually slams into the nucleus of one of the atoms of ice there, and that produces other particles which then produce some light, and you can detect the light.
Yeah, that's right.
I see. All right, so this neutrino came from an object that could be pinpointed on the sky, and it's called a blazar. A blazar. So can you tell me what a blazar is?
Yeah, a blazar is an active galactic nucleus, so this is a certain class of objects. And the particular thing about the blazar is that it emits radiation in jets perpendicular to an accretion disk, and these jets are pointed towards the Earth. And this provides an environment where it can accelerate particles, and if they escape, then they can come to Earth, and this is what happened. And the neutrinos are the ones that can really travel out of this environment.
It's like a quasar, really, but it just happens to be, pointed our way.
Exactly.
But this particular blazar, I'm told, is almost 4 billion light years away. I mean, that's a long distance. Now, what can you learn about the blazar from this one neutrino? I mean, all you measure is a path of light through the ice, so you know where it's coming from, and I guess you know the energy. But what else does it tell you?
So what you can learn from one single event is actually limited, because of course you would like to have more. You would have to like to have more over several periods of time. We hope to learn what the processes are that accelerate these particles and make a connection between the acceleration that produces neutrinos in the end and the acceleration that produces the cosmic rays that we also measure here on Earth with experiments, and the high energy gamma rays. And we try to find out how this all works together and what the processes are that accelerate these particles.
So in fact, you're studying this thing, or can study this thing, not only by detecting neutrinos, but other particles, cosmic rays you mentioned. Is that why physicists get all excited about the era of multi-messenger astronomy, as they call it?
Yes, that is exactly why, because it opens a new window to the universe. Like previously, you had the opportunity to watch the sky in different wavelengths of photons, everything from infrared to X-ray and high-energy gamma rays, and now basically we're adding the neutrinos, so we can learn information that was hidden before.
Now, there are a lot of puzzles that neutrinos might conceivably solve, including one that's pretty deep, like why is there anything instead of nothing in the universe? Do you think IceCube is going to help us address that kind of question?
Well, if you're talking about the neutrino antimatter asymmetry in the universe, we have different experiments than IceCube that are particularly targeted to measure things like this, like the deep underground experiment Dune that we're setting up here at Fermilab.
Tell me about Dune. It sounds like a sci-fi novel.
Yeah, so Dune will use neutrinos, but doesn't wait for natural neutrinos to arrive at a certain time, and then you have to be lucky to catch them at the location where you are. For Dune, we will produce the neutrinos ourselves. We produce high-energy neutrinos in our accelerator complex, and we will produce this beam of neutrinos and send it from Fermilab, where we produce it with the proton accelerator, to the location where we put our experiment, and that will be in South Dakota in an underground mine, so it's going to be shielded from a lot of background processes.
Finally, Anna, it's taken some extraordinary instrumentation to detect neutrinos. What do you see as the big picture reason for learning more about these tiny particles? Obviously, it's academically interesting, but, if you could jump into the future 20 years, what do you think we'll know about the universe from studying neutrinos that we don't know now?
So the neutrinos are kind of special because they're not really described of what we right now think is the world of particle physics. So we have a standard model that gives us all the particles we have observed so far, but the neutrinos don't really fit into that model. For example, we thought initially neutrinos would be massless, and that turned out not to be the case, but they're so light that we're not yet able to measure their masses. So that's a problem we need to solve. We need to know where they come from. We need to know how they, what we call, oscillate. We have 3 types of neutrinos, and they seem to change from one into the other. And we want to understand that pattern, why this happens. And all these things would change our model of standard physics, and that ultimately has an implication on how the universe evolved and how it created and formed all the particles and then all the matter and the structures that we see today.
From what you've just said, it sounds like it could turn out that neutrinos have shaped the universe in such a way that, maybe we wouldn't be here if it were for neutrinos.
That is true, because we think that during the Big Bang, matter and antimatter was created in equal parts. So scientists are trying to understand why we came to an excess of matter, as it seems, in the universe.
In other words, the reason that there's something rather than nothing may be ascribable to neutrinos.
Well, yeah, what we're trying to do is to find if there's an asymmetry between how neutrinos and how antineutrinos behave. And then this can be connected to the evolution of the universe.
Anna Schukraft, thank you so very much for speaking with us.
You're very welcome. Thank you.
Anna Schukraft is a physicist at Fermilab National Accelerator Laboratory in Illinois.
Now, neutrinos are clearly important to the story of the cosmos, but could we possibly study them without having to build an instrument a kilometer on its side in one of the world's most inhospitable locales?
Imagine pouring a cup of coffee, taking a seat, and hunting for the secrets of the universe at your desk. Physicist Ephraim Fishbach believes he has discovered an effect that will allow him to build a desktop neutrino detector.
Exactly. This is a complete accident and a complete surprise. What we're finding is that it appears that radioactive decays of certain radioactive elements are very sensitive to changes in the flux of neutrinos from the sun. Now, why would that flux change at all? Well, we know that the sun is closer to the Earth part of the season and farther away from the Earth other times. And so that causes a slight change in the number of neutrinos that hit the Earth, every second. And we find that radioactive decays sense this, and that's the new secret that we're trying to work out.
So you have some sort of, plate made out of one of these radioactive metals, and you just have some sort of meter at the end of it, and you measure how many neutrinos are going through it?
That's right. We're not actually measuring the neutrinos coming out. What we're measuring is the change in the rate at which the radioactive sample undergoes decay, how many decays it does per second, for example. And we find that there's a different rate in the summer and the winter. There's a different rate, depending on where you are on the Earth and so on and so on, all of which point to the fact that somehow or other, the neutrinos coming from the sun are influencing this radioactive decay in a way that we don't understand. But that, as a fact, it seems to be true.
This sounds like one of those things that you characterized by saying, important if true. You're convinced it's true.
We recognize that this is not proven yet, that there are many, many legitimate questions which have been raised, and we've attempted to answer all of them. But at the moment, we see no objection to what we're doing. We recognize that this is a very, very strange and unusual effect. But as we continue to look at the data point out effects which, so far as we can tell, can only be explained in that way at the moment, even if we do not have a fundamental theory. That's correct.
I think a lot of people will remember the claim of cold fusion by a couple of physicists in Utah years ago, and immediately several dozen teams of researchers ran to their labs and tried to replicate the experiment. Has the same thing happened for your observations? Have people been trying to reproduce your results?
Many groups are trying to replicate our experiments. We and various collaborators are doing it. But to be fair, there are people who are trying to replicate our experiments who are not agreeing with our results. And these are very complicated experiments, and there can be legitimate differences arising in part from the fact that people are using different radioactive isotopes and measuring them under different circumstances. So this is an open question. I should make it absolutely clear. We are not claiming to have proved this as a physical fact. We're hoping for the best. But right now, one way or another, it's an exciting discovery. Either we'll find out that it's wrong for some reason, there's something funny going on that we don't understand, which itself is a learning, or, as I expect, we will learn that there's a new effect. And one should keep in mind, the very existence of neutrinos was considered crazy in 1930 when it was proposed by Pauli, but neutrinos have managed to surprise us decade after decade, year after year. I'm hoping that this will again be one of those great surprises.
Ephraim Fishbach, thanks so very much for being with us.
Thank you again for the privilege of being here.
Ephraim Fishbach is a professor of physics at Purdue University.
So the amazing thing that Professor Fishbach has discovered is that neutrinos apparently have an effect on the radioactive decay of certain elements.
Interesting that a particle that has no mass and no electrical charge could have an effect on radioactive decay. I thought one of the defining characteristics of neutrinos is they don't interact with anything.
Well, exactly. But as you heard, he himself is puzzled, and he doesn't understand why it should. Nobody's explained it. But if it's true, then, he can build this desktop neutrino detector. And, that would change everything, because then you could have lots and lots of neutrino experiments around the world. We'd learn sooner more about them. So you see that neutrinos have followed this path from being a puzzle, where was some missing energy, to a prediction that sounded ridiculous, to something that was actually discovered, to something that's now being studied, and that in the future may turn out to be critical to a whole bunch of interesting problems. Einstein came up with the idea of a collapsed star with a gravitational pull so strong that even a beam of light couldn't leave it. Well, he thought his idea too preposterous to be real. Einstein was wrong.
What cosmic monster is the place where gravity runs amok? You know what it is, and it's next.
Radical Cosmology on Big Picture Science. Albert Einstein wasn't often wrong. On one occasion, when he thought he was wrong, he was actually right, although he didn't know it at the time. But, you got to cut him some slack. That theory of general relativity of his predicted some bizarre stuff.
So Einstein's theory of general relativity predicted gravitationally collapsed objects whose gravity was so intense that nothing could escape, even light. But he didn't believe the predictions of his own theory. He thought they were an unspeakable creation of physics.
We've been talking in this episode of Big Picture Science about ideas in astronomy that were so ahead of their time, they challenged the very nature of what we imagined was possible. That was certainly true about these objects whose gravity is so intense that nothing escapes them.
Einstein's Monsters, The Life and Times of Black Holes, is the most recent book for Chris Impey, a professor in the Department of Astronomy at the University of Arizona. Once thought impossible to exist, now we know black holes are the result of a collapsed dying star, and ubiquitous. Very large ones are found in the center of nearly every galaxy. These guys are endlessly fascinating, including for the movie-going public.
There is an inexorable force in the cosmos where time and space converge, swallowing everything in its path, radio waves, light, even planets and stars.
The study of black holes, like the study of neutrinos, is intimately linked to our understanding of the universe, says Dr. Impey.
Chris, we heard that Wolfgang Pauli's prediction of the neutrino was done after looking at some experimental results. Black holes were predicted on blackboards, not as the result of an experiment. It was a product of the mind, correct?
That's right. People worked through the brand new theory of general relativity and predicted the existence of extremely compact stellar remnants from which nothing could escape.
Gravity's apparently not strong enough to pull me through this chair I'm sitting on and all the way to the center of the Earth, but somehow it can pull 10 million billion pounds of star into something smaller than a pinhead, smaller than an electron, and yet they talk about gravity as being the weak force.
Right, it is the weak force, but, a star is a pretty massive object. That's sort of trillions and trillions of tons of mass, and once the fusion is over in a star, which is the only thing that keeps the sun and all the other stars puffed up at some large size, like 1 million kilometers across, then gravity will just crush them right down to a very small size.
So what's happening there is that gravity, weak as it is, of course it's relentless, and it just eventually can sort of overcome every other force of nature?
Yeah, and actually it's a sort of a positive feedback thing because gravity is an inverse square force, so the closer two objects are, the stronger the gravity between them. So as the star starts to collapse, the gravity gets stronger, which means the force inwards gets stronger, so it collapses faster, and it's a runaway gravitational collapse. So the whole thing actually accelerates.
I see. Any idea about how long that collapse takes? I mean, if you have a big star, much bigger than the sun, and it runs out of fuel and collapses, I mean, is that something that happens in minutes, days, millennia, millions of years? What?
I think we didn't really know until computers got really good and fast about 20 or 30 years ago. And now what they can do is simulate a supernova, the death of a massive star, where the core collapses. And the free fall collapse of the core to a black hole state, it literally takes minutes. It's very fast.
That would be dramatic to witness, I suppose. Can you give us some top reasons why black holes have garnered the title of being one of the most enigmatic phenomena in the universe?
I think it's because the veil that nature has drawn over them with the event horizon. So bizarrely, we have no idea what the state of matter inside a black hole really is, because the event horizon just is the edge of our knowledge. And also within the black hole, according to the theory, one of the reasons Einstein detested them is a singularity, which is an infinite cusp of density, which makes no physical sense. So black holes have some strange properties that are still not understood.
And yet you write that if we want to understand our place in the universe, we need to understand these enigmatic monsters. Why is that? I mean, it's more than just personal interest.
Right. Well, black holes are pretty rare because only massive stars die that way. So really a tiny fraction of all stars will end up as black holes. I think as far as the universe goes, the black holes that are of interest are the ones at the centers of every galaxy, because they actually play a pretty big role in how galaxies form in the first place and then evolve, of how stars form in a galaxy, and that's a story that in the end involves us.
It's interesting to me that black holes were first considered by some of the same physicists who, a few years after they were working on that problem, were working on the atomic bomb. But, they were just considering the possibility. How did black holes go from being an exotic mathematical, trick on a blackboard to a real astronomical object?
It took decades because the only way they were discovered was because a black hole can be in a binary system. An isolated black hole, there's nothing to see. And the same with neutron stars. Neutron stars were also predicted in the 1930s and not discovered until pulsars became the telltale radio emission from a subset of them. So this subset of black holes that are in binary systems sucking gas off their companion star gave X-ray astronomers a way to find black holes, and that's who found them first in the late 60s.
So what you're saying is that while you can't see an individual black hole, you might be able to see it eating something.
That's right, and that creates the irony that these dark objects are some of the brightest objects in the universe when they are eating something, when they have a companion, or in the center of a galaxy when they're chowing down on gas and stars.
If you're a fan of sci-fi, you'll often see that, well, to begin with, that characters just love to dive into a black hole. But funny things happen there, including funny things that happen to time. What does happen to time when you get near and into a black hole?
Yeah, the relativity is very interesting there. So if, say, you and a buddy went to the vicinity of a black hole and you drew lots and you got the short straw and you had to go into the black hole, as seen by your friend, you would take an infinite amount of time to reach the event horizon. Essentially, you would be frozen at the event horizon and your light would be redshifted as well, so you'd have a reddish tinge. However, to your perspective, you just fall right into the event horizon and will probably be killed or to an unknown fate. So there's not a reversibility there. The experience of the infalling person and the person watching from outside is quite different.
So from their point of view, you're falling into that black hole forever. From your point of view, it's all over quickly.
Right. And there's an implication of the perspective from outside that's led to this idea. It's called the Holographic Principle. Stephen Hawking wrote about this and others. The idea that even though matter is entombed in the black hole and can't get out and information can't get out, perhaps the information of what's in a black hole is somehow inscribed on the event horizon like a hologram.
We can't see a black hole directly, but there is something called the Event Horizon Telescope, and it is purported to be able to see a black hole's shadow. Now, what can that possibly mean?
That's a very exciting project, and some of my colleagues in Arizona are a part of that collaboration. It's a network of radio telescopes designed to take the sharpest images ever made at sort of millimeter wavelengths. And they're looking at the center of our galaxy, at that big black hole. And the reason they're using radio telescopes is because we can't see the center of our galaxy in visible light. There's too much dust. Photons don't get out of the center of our galaxy, visible ones. So they're looking at radio waves, and they have the sharp imaging with their array of telescopes to potentially resolve the event horizon, and they can see the shadowing of the event horizon on the underlying gas or the background gas that's very hot. And that will let them test general relativity in a completely new way. Very exciting science. And it could happen, those first images, as soon as next year.
Now, black holes can be formed when a giant star dies. You've mentioned that. But there are also really big black holes in the centers of galaxies, much larger than, you'd get by collapsing a star. Where did those come from?
That's still an active area of research. And, my research really wasn't on their origin. It was on their properties and how they become bright. There's a sort of chicken and egg situation. Nobody knows in the early universe, first few 100 million years after the Big Bang, whether galaxies formed first, their first little groupings of stars by gravity, or the seed black holes formed and aggregated stars around them. After they form and a galaxy gets a black hole, the things evolve together. Because when galaxies merge, the stars combine and form a more massive stellar system, and the black holes literally merge and form a bigger black hole. But which came first is still a very open question, which actually the James Webb Space Telescope is partially designed to answer.
I see. So it's a chicken and egg problem whether the black holes come first or the galaxies come first. I think that a lot of people have heard about the enormous gravitational pull of a black hole and figure that, well, if there's this big black hole, millions of times the mass of the sun, just sitting, lurking in the center of the Milky Way galaxy, that might pose some danger to us. Does it?
Not really. One of my little agendas is to try and take black holes off the worry pile. They're sort of like the misunderstood children of astrophysics. People are scared of them and worried about them. Well, first of all, they're very rare. So, you'd have to inspect about 1 million stars around the sun before you found your first black hole. And even the big ones at the center of galaxies, our galaxy has a 4 million times the mass of the sun black hole. And far from it, as we are, 25,000 light years, we really can't tell there's a black hole there. The gravity from that distance is very modest. You really have to be very close to a black hole before all the weird and scary stuff happens.
Now, famously, Stephen Hawking tried to understand exactly what goes on inside a black hole. Kip Thorne down at Caltech has done. What kind of puzzles could we solve if we understood what goes on deep inside a black hole?
Well, the intriguing thing is, of course, what happens to time, which we've already talked about. And as you approach a black hole, time is massively distorted or dilated or slowed down. In principle and in theory, Kip Thorne's written about this too, inside a black hole, if it's rotating, you can have what's called a time-like curve where if you could survive falling in, like with a big one, you could move around that time-like curve and see past and future versions of yourself. So that's sort of time travel within the black hole itself. And wouldn't it be nice to know if that actually happens?
And could you travel to another universe? There's more than one universe?
That part is also more speculative. White holes and gravitational theorists have written about that as a possibility. It's allowed, it's not ruled out, but we have no evidence that happens. As far as we know, the black holes we've seen just seem to be tombs of matter, and they don't poke out anywhere else in the universe.
You write that black holes will be the last objects remaining at the end of the universe. What do you mean by that?
Yeah, that's part of why they have a deeper significance in cosmology and in astronomy. In the very distant future, first of all, in about 1 trillion years, all the stars will be dead. So the cycle of star life and birth and recycling of material to make new stars is just eventually going to run out of steam, and stars will die and be corpses. Then, on an even longer timescale, galaxies will sort of evaporate, and we think normal matter will evaporate if standard physics is correct. And so the last repositories of matter in a fixed state are going to be black holes. And then, according to Stephen Hawking, even they evaporate and disappear. But that takes an incredibly long time. So they are the last objects standing in the universe.
Chris Impey, thanks so very much for speaking with us.
I've enjoyed it, Seth. Thanks.
Chris Impey is professor of astronomy at the University of Arizona, and he is the author of Einstein's Monsters, The Life and Times of Black Holes.
So the big picture here in the show is that this repeating pattern in science where somebody has a really radical idea, either because of an experiment or they're just thinking about things, and, they're reluctant to present it, and people are reluctant to accept it because it is radical. And then somebody can do an experiment and prove, hey, you know what? He was right. She was right. And you learn something and you go forward and you forget that this was all heresy when you started.
Thanks to the members of our team with radical talent, senior producer Gary Niederhoff, assistant producer Sarah Derwin, and operations manager Barbara Vance. I'm executive producer Molly Bentley.
Thanks also to financial support from Rena Shulsky David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life. I'm the Institute's senior astronomer, Seth Shostak, and a big thanks also to our listeners.
Your ears have been attuned to an episode of Big Picture Science called Radical Cosmology. If you'd like to hear more Big Picture Science, well, you'll find past episodes in our archive at bigpicturescience.org.
And if you never want to miss an episode, subscribe to PyPySci on iTunes, Google Play, Stitcher, Spotify, iHeartRadio, and Pandora. And you can also find us on the new platform, Himalaya.